Good day. My name is Michael Dow Jr., and my mentor is Dr. Antonino Cucchiaro. Our project is algorithm optimization for fast transient identification in the deeper, wider, faster data. I'll begin by giving you a brief overview of what the Deeper, Wider, Faster program is. The Deeper, Wider, Faster program, or DWF, includes over 40 different observatories which together can observe a much wider area of the sky than would be possible with a single telescope. They observe in a large portion of the electromagnetic spectrum, including visible light, gamma ray light, infrared light, and also radio waves. DWF focuses on the detection of fast transients, specifically counterparts to fast radio bursts, or FRBs. The graphic I have on the right shows all the different facilities included in the DWF program. This includes satellites such as the Swift telescope and ground-based observatories such as the Ettelman Observatory in St. Thomas. Fast transients are astronomical objects whose brightnesses drastically increase and decrease over a short period of time. These objects include FRBs, fast radio bursts, gamma ray bursts, and supernovae. Events like these can last as long as a few hours to as little as a few milliseconds. We are studying these objects because supernovae are fundamental to understanding the catastrophic ends of stars 10 times larger than our Sun. Gamma ray bursts may be the only objects that can help us understand the first stars ever born in the universe, and fast radio bursts only a relatively recent discovery, so their origins are still unknown. The goal of this project is to develop a Python-based algorithm that can be run on a supercomputer that will access the data stream during the DWF observations, build light curves that display these brightness spikes versus time, such as the one I have on the right, and quickly identify those objects of interest so they can be studied quickly with more powerful, dedicated facilities. These two plots I have are two examples of what program that I wrote has been able to do so far. It takes the data from the DWF file and plots the time versus the magnitude. In astronomy, the smaller magnitude value actually translates to a brighter object, and the time used in astronomy is a modified Julian date. So far, the program I have written can read the data from the DWF files, plot the brightnesses versus time, convert the modified Julian date values into seconds so they're more understandable at a glance. Create a model for decaying light curves. Those are light curves that have a negative slope. And determine the decay index alpha, which tells you how fast these objects eventually disappear. The graphic I have on the left shows a before and after of when I initially started and where my program is at now. The one at the top shows just the MJD values versus the brightness, while the one at the bottom converts the MJD to seconds and also displays the model of the light curve with the decay index. Our next steps are to continue working towards an algorithm that can run simultaneously with the DWF survey and extract light curves of objects of interest. Our immediate next steps include creating models for all light curves with no inflection points, extract all the parameters from the model, such as the decay index and the accuracy of the model, and put them in a separate file for each iteration the file is run, and select the fastest decaying objects that can be either gamma ray bursts, fast radio bursts, or other unknown sources. Please send any questions or comments to the email address on screen, and thank you for listening to